When cooled down below a critical temperature, ensembles of trapped bosonic atoms form a Bose-Einstein condensate. Due to interactions between the atoms, collective excitations of the condensate exist. Quantized excitations of this type are called quasiparticles. In our article, Modulated Light Potentials for State Manipulation of Quasiparticles in Ultra-Cold Bose Gases, we investigate the coupling of the condensate to laser light in an optical cavity. We assume that the laser light frequency is detuned from an atomic resonance and couples to the atoms via the same gradient force that is used for optical tweezers. By modulating the light intensity, it is possible to create excitations in a quasiparticle mode that has the same wavelength as the intensity modulations of the standing light wave. This effect corresponds to the direct driving of density oscillations by the modulated light potential. Comparing this situation to a swing, direct driving corresponds to pushing the swing. Resonance is achieved when driving frequency and eigenfrequency of the oscillator are equal. We give a derivation of a Hamiltonian description for this process from first principles. Direct driving corresponds to the leading order term, which is linear in the quasiparticle mode operators. We show that higher order contributions can be used for other driving processes. For example, parametric driving can be applied when the laser light's modulation frequency is twice the frequency of the quasiparticle mode that is to be addressed. This leads to single-mode squeezing. Comparing the situation again to a swing, parametric driving corresponds to a periodic change of the swing frequency. Another process that appears is mode coupling, where for example excitations can be pumped from one mode into the other. This can be applied like a beam splitter or mirror operation in frequency space. Mirror operations can be used to swap the states of two quasiparticle modes. With the beam splitter operations, a Mach Zehnder interferometer in frequency space can be constructed. We present two explicit example applications in sensing: the measurement of the atom-atom interaction strength, represented by the scattering length, and the measurement of an oscillating force gradient. We propose a specific implementation based on one-dimensional condensates of potassium atoms and state-of-the-art experimental parameters. While our results suggest that modulated light potentials can be useful for coherent state manipulation of quasiparticles in ultra-cold Bose gases, we find that for sensing applications, major technological advances are necessary for the method to become competitive.